And the question becomes, what is the probability you reach, say, 0 before you reach n? And so if you start calculating all the different possibilities, this can become quite involved. And so, does anybody have any idea of how we should attack this? Yes.
Wait, so you have a 50% of
moving one unit.
Moving one unit at any given okay.
At any given moment, all steps are independent of all other steps.
Okay.
And so, does anybody have any ideas on how to attack this problem?
Well, it's reliant on the position k to start at.
So it will depend on where you start. So can you give me any k or any n where we understand what's going on?
If n's 0 or 2,
Okay.
you know, then every choice is pretty simple.
Okay, so if n is 0, I'll even put in 1. 1's not so bad. Or 2, there's no difficulty. What's the next easiest n to study after 0, 1, and 2?
4.
4. So 0, 1, 2, 3, 4. In this configuration, which is the easiest point to study at first? 2. What's the probability you reach 0 before you reach 4?
50%.
Right. Write 50% in a better way.
0.5.
Write it in a better way.
1 over 2.
Right, in a better
2
way.
over 2 over 4.
2 over 4.
2 over 4.
So the probability you reach 0 before you reach 4 is 2/4. What's the probability you reach 0 before you reach 4, given that you start at 1?
4 minus 1 over 4.
Why 4 minus 1 over 4?
I'm just trying to not say it in terms of like 3/4, because 3/4 is not really the most enlightening way to do it, but I think that that it is. It might not be 3/4. That was just a guesstimate.
So how do we figure out? Okay, why 3 over 4?
1/2 times 1 and 1/2 plus 1/2 times 2 over 4.
Good. Yeah. Half the time we go straight to 0, and then half the time we go to 2, and once we're at 2, we have a 50% chance of coming home. And so that will give us 3/4. Well, if this is 3/4, by symmetry, what's 3?
3/4.
1/4.
Oh, you're going to 0.
Right, going to 0.
I was thinking about going to either end.
Right. No, the whole point is we want to know what's the probability we reach 0 before we reach n. So if I give you 0 to 4, it's not so bad. What if I gave you 0 to 8?
Similarly.
So which one would you do first?
4.
4. And 4 would again be
4 out of 8.
4 out of 8. Now what's next?
2 and 6.
2 and 6, and this would be
2 out of... Oh, sorry. 6 out of 8.
6 out of 8.
And then 2 out of 8.
And 2 out of 8. And now how do we get 1?
Similarly.
1/2. Well, that's 1/2.
So,
Plus 6, 8.
which is 1/2 plus 1/2 times 6/8. Right? And that will be...
7.
Yeah.
You can just gamble and hope that that's right.
Could it possibly be 5/8 and 3/8 and
Could it be? Yes, but if you do the algebra, the answer will be no. I mean, I think intuitively it seems reasonable. It should be larger than 6/8, because... So why can you tell me it's going to be larger than 6/8?
Because
it's
if you move to the right, which is already a lesser chance, then you're already working from the probability of 6/8.
Right.
So is it 1/2 of 6/8 plus 1/2?
Although I said that in the most standard way.
So it's 1/2 plus 1/2 of 6/8.
You're talking about different locations.
Right? And so when you do this, 1/2 is 4/8 plus 3/8 is 7/8. But if you think about it, it's got to be larger than 6/8. As was said, we're starting off, closer to 0 than 2. And at 2, the probability was 6/8. So it shouldn't be lower from starting further away. So, what about 3? 5/8. And so if you just,
I was
continue...
talking about 3.
Oh, you're talking about 3? Oh, okay. Well, then if you're talking about 3, then that would explain why you're getting an answer.
I was so confused.
Okay.
I was talking about 3 and 5 being 5 and 3. Filling in the 2 spaces we hadn't done yet.
I see. Oh, I see. Okay, as opposed to the one we were still in the process of doing.
Well, we'd written down an answer I thought we were done.
Okay.
Oh.
No,
okay,
it was,
so it was what I thought.
we were exploring why the answer was what we thought it was. Okay, so now, what would be the next one to look at after 8?
16.
16. And then after 16? So can we get? So do we agree that we can get all the powers of 2 without too much trouble?
Yeah.
Basically, you get the middle, and then you keep filling in. You keep doing midpoints. Okay. Well, what if we don't start off with something that's a power of 2? What if we start off with just 7? How would we get 7?
Well, you want to start from try and start from somewhere in the middle. I guess a place that you can start is you could notice that if you go, the probability of reaching 0 from 3 is the same as the probability of reaching 7 from 4.
Okay, good.
And then you...
No, it's not,
It's not?
because... Oh, wait, 0 from 3 is 7 from 4, yeah.
Yeah.
Alright. I thought 4 from 7, and I was confused for a second.
So it's a good. What you have is a really good observation, which is a good start. How do we finish it?
By... What if you keep doing that out, like, because we know 3 and 5 are similar, and each point, like,
So
if
3 and 4 are similar.
the same sort of
So I
logic
could
we
call
use to
this
find the unknown.
x and 1 minus x.
And then 2, like let's say that 3 has 2 options. It has a 50% of option of going to 1 minus x, and it has a 50% of option of going to 2.
But then I need to know what 2 is.
Yeah.
So it's getting very
2 is
involved.
similar to 5.
So 2 is similar to 5,
Yes.
but this is becoming a nightmare, right?
Especially if you had to do this for a larger number than 7.
Right. So let me show you a fast way to do this. So here's the fast way of doing this. We're going to proceed by induction. So assume if I have from 0 to n minus 1, if I start at k, the probability reach 0 first is n minus 1 minus k over n minus 1. So let's assume we know it when we only have n minus 1 locations. Okay? If we just have 1, 2, or 3, we can just do these by brute force. It's not so bad to build intuition. 0, 1, 2, k, n minus k, n. Okay? So your idea of pairing off k with n minus k is a very good idea. Let's call this probability x. What's the probability at n minus k? 1 minus x. So, what is the probability we reach 0 before we reach n minus k? Yes?
In our first expression for if we have 0 to n minus 1,
Mm-hmm. So if k equals 0, it's 100%. If k equals n minus 1, it's 0%. So what's the probability we reach 0 before we reach n minus k? So we just plug in n minus k to our formula. The answer is n minus k over n minus k. The whole point is this is going to be shorter. The only way it wouldn't be shorter is if n minus k equals n. Well, if n minus k equals n, then we're starting at 0, and we want to know what's the probability we reach 0 before we reach n. We can do that. We're starting at 0. So we know if we start at k, we'll get to 0 before we get to n minus k this % of the time. Now that we're at n minus k, what's the probability we reach 0 before we reach n? Well, that's just 1 minus x. And we get an equation for x. X is equal to n minus k over n minus k. Did I make a mistake?
Shouldn't there be a 1? Shouldn't there be a minus? Yeah. A minus 1 in the denominator?
No, because we have n minus k slots.
Oh, okay.
Probably
You
get
started
Right.
with minus 1.
Really,
Yeah.
what we're doing is
I see.
we're doing a strong reduction. I'm replacing n minus with n minus 1, n minus 2, n minus 3. I could do any of those,
Okay.
and I'm fine. So what's the probability I reach 0 first? Well, first I could calculate the probability I get to 0 before I get to n minus k, because if I'm going to get to n, I've got to get to n minus k first. Now that I'm at n minus k, what's the probability I've reached n minus k before I reach 0? Since this was n minus 2k over n minus k, it's got to just be k over n minus k. Right? Because these two probabilities have to add to 1. So if I reach 0 first from k, n minus k over n minus k times, then I reach n minus k before 0, k over n minus k times. And now the probability that I get to 0 first before I continue all the way on to n, we're just calling that 1 minus x. And now we can just solve this with algebra. So we multiply through by n minus k, and we get n minus k times x is n minus 2k plus k times 1 minus x. I have a negative kx, I have a negative kx, those cancel, and I get nx is equal to n minus k, or x is n minus k over n. So this is another way to see the answer. Okay, this is another example of, I think we're calling it the bring it over method. So it's very similar to a memoryless process. It doesn't matter how I get to a certain point, it just matters, am I at that point? And if you want to go through all the different complex ways to explore, it can become a nightmare. This is very similar to the bug problem we did. If you look at these problems the right way, they become extremely elegant. It takes a long time to find the right way of looking at these problems. But when you do, it becomes very nice. This has applications in finance. People often use a random walk model for stock prices, or maybe some kind of gambling. What's the probability your stock crashes before you make a certain amount of money and get out of the market? And so, calculations like this are extremely important. If I start off with a stock at 58 and I just want to go until it's 60 and then sell, what's the probability it makes it to 60 before it goes all the way down to, say, 54 or something like that? You can phrase it in those respects. And then what's nice is we have a beautiful method if n is a power of 2, but I don't really know how to make that fill in for the other values of n. But this way works for all n at once. Yes?
Could you explain again how we're using induction?
Well, what I'm saying is I need to know what's the probability I start at k and hit 0 before I hit n minus k. So that's using fewer positions. We're looking at something with n positions. Now I'm looking at the restricted problem with n minus k positions. So I'm assuming I already know how to do that. Technically, this is the strong form of induction. Normal induction, I would only look at n minus 1. But here, I'm really looking at n minus l for any l less than or equal to n minus 1. So I'm assuming I know how to do the problem when I have fewer locations. If I just have one location, the problem's trivial. I'm always at 0. If I have 2 locations, again, trivial. If I have 3 locations, the only one that's difficult is if I'm in the middle. Well, that's a 50% chance. So I can do small cases just by brute force, and just calculating things and doing the recursion things we talked about. But for the general case, if I try to see going straight to 0 or straight to n, that's a little bit hard. If instead I look at just going to 0 or just going to n minus k, I've reduced it to something I already know how to do. But of course, if I get to n minus k, have I lost?
No.
No. I only lose if I get all the way to n. So getting to n minus k is not considered a loss. But I can use this to then analyze the rest of the problem. So I really like these problems. These are great examples of memoryless processes. Okay. Any other questions about that before we shift gears? So I'm not quite sure why the file was not displaying. It had been uploaded according to my file over there, but all right. So what I want to do is I want to explain the method of least squares. This is one of the great examples of probability. So imagine I have some data set like this, and I want to try to find the best fit line to this data. So humans are not horrible predictors in situations like this. You can look at this and get some idea of what's going on. Can you give me an estimate for the slope? Can you give me an estimate for the intercept? I'm sorry? The intercept is where?
The origin.
Okay, so the intercept is the origin. And what about the slope, if you had to guess? 4, 2, wildly different answers.
5.
So if I go for 100, 100 looks like it's around 20. So I would go with 5. So, you know, again, I've also seen the file several times. And so I actually drew the data from xn was 5 plus 0.2 times n, yn was 5xn, and then I chose an error randomly from a normal distribution. And so the best fit line, and I'll talk a little bit about how to find the best fit lines in a moment, is about 4.99x plus 0.48. And so here, it does a really good job, the method of least squares does a really good job of finding the slope. It doesn't do as good of a job of finding the intercept. If you had to, which number do you think is more important, the slope or the intercept? The slope. As your data gets bigger and bigger and bigger, you know, as your value over here gets bigger and bigger and bigger, the intercept is going to have a negligible effect on it. But the slope is going to be quite significant. So the question is, what is the method of least squares? How does it work? What kind of problems can it solve? It all comes down to methods of studying error. So there are 3 types of error functions. So the first, I'll call it E1. So here's the setup. Data will be pairs xn and yn. And we predict yn is axn plus b. So we predict a linear relationship between the input variable x and the output variable y. So one possible error function, and it's going to be a function of our a and b, is just the sum, and it goes from 1 to n, of yn minus the prediction. So can somebody give me an issue with this measurement of error? We're going to have to be a little bit fast today because we've lost a lot of time for things loading. Yes?
They'll cancel.
Yeah, signed errors. So you have the ridiculous situation. Imagine these are your 2 data points. And I want to find the best fit line between these 2 data points. This line would have 0 error. Right? We don't want errors to be able to cancel. So E1 is quite bad. All right, can somebody give me a nice fix so I no longer have errors that cancel?
Absolute value.
Absolute values. Now I no longer have errors canceling. What's bad about absolute values? We lose calculus. So here, errors cancel. Here, we lose calculus. The absolute value function is not differentiable. Since it's not differentiable, all of the truths from calculus are unavailable. So, what would your third guess be?
Squares.
Squares. And, oops. And what's the title of today's lecture? The method of least squares, right? So we can use calculus. Instead of squares, what else could we have used? We could have used fourth powers. The issue with the method of least squares is it magnifies errors. So it's much worse to have one error of 2 than 2 errors of 1. The method of absolute values treats all errors equally. 2 errors of size 1 is the same as an error of size 2. This method, if you have one data point where, for instance, somebody's sneezing as they collect data, and you had one data point that was all the way up over here, that one point would draw the line enormously. And so that's the big issue with using the method of least squares. If you have a sneeze data point where something is up here, you would hopefully find some way to justify removing it. If you look at the values we got, using the method of least squares, and I'll show you how you compute these values in a moment, we get the best value of A is about 4.99 and B is about 0.48. If instead we use absolute values and find the best fit values for A and B, we get 5.03 for the slope and something less than 10 to the negative 10 for the intercept. So the method of absolute values does a much better job of capturing, I would say, the true behavior of both parameters. In an advanced stats course, you're going to actually talk about error bars on these values. When I say this is A and this is B, okay, that's what I get when I apply the method of least squares. How confident am I? I want to know something about the standard deviation of these values. Maybe I want to know 95% of the time my true value for the slope will be between 4.95 and 5.05. I want to have an idea of how much fluctuations I could expect. Okay, and so as I said, the difference between these two methods is the best fit value of B, which is typically the least important of the two, is much better in the method of absolute values than it is in the method of least squares. I'm going to risk turning off the projector. What I want to do now is go through the algebra as to how you would find the best fit values of A and B. Now right now, the way I framed the method of least squares, it only works if you have a linear relationship. This should seem quite restrictive. I will show you that you can actually find a linear fit to almost anything that will occur in science and the world. So how would we find the best fit values of A and B? What would we use? Got to answer fast today, we've lost time.
You want to minimize that?
Yeah, we want to minimize. So how do we minimize? Take derivatives, right? There's a reason why Calc 3 is a prereq for this class. There's a couple of key moments where we need to use it. I have a function of two variables. How can I find the minimal values of A and B? Use calculus. Now what's really nice is if you send either A or B to infinity, you can make the error as large as you want. So when we do calculus and minimization, we will definitely be getting the minimal value of the error and not the maximal value of the error. So we want to say dE3 dA equals 0, partial E3 partial B equals 0. So we're taking the derivatives with respect to A and B. So everything I'm going to do now is in the notes I've posted online on the methods of least squares. So if you don't want to write the algebra, by all means, just follow what's going on. There is a lot of algebra. So the first one gives us the following. So we have a sum, n goes from 1 to n, and now we have the derivative of this. We're going to get 2yn minus axn minus b, and now when we take the derivative with respect to a, inside here we have a negative axn, so we get a negative xn coming out. Right? And the other one is the sum n goes from 1 to n of 2yn minus axn minus b, and now when we take the derivative with respect to b, we just get minus 1. Alright, the first thing to note is, can I remove the factor of 2? Yeah. Can I remove the negative sign? Yeah. So I can remove all those, and now what I'm left with is bringing things over to the other side. The sum, n goes from 1 to n, of xn squared times a, plus the sum, n goes from 1 to n, of xn times b, is the sum, n goes from 1 to n, of x and y. So I'm just bringing the xn inside, And then because I have sums, and a doesn't depend on the index of summation, I can just pull the a's outside. For the other equation, I'll get the sum of xn, n goes from 1 to n, of a plus the sum n goes from 1 to n of 1 times b equals the sum n goes from 1 to n of yn. And again, I'm just pulling these over to the other side. What does this look like?
System of equations.
System of equations. Two variables, two unknowns. It turns out, unless you are a complete idiot, this will always be solvable. There's only one thing you can do. Only one thing. And while I might have specific people in class I would like to ask right now, I will throw it open to the class. What is the one thing you have to avoid in choosing your x's to make sure that this is solvable? There's only one thing you can do. So you're trying to figure out how y depends on x. There's just one thing to avoid. What is that one thing? You've got to give me n values of x.
They're all 0.
A little bit more general than they're all 0. They're all the same. As long as you don't give me the same value every single time for x. I want to see how y depends on x by always evaluating at the same value of x. You're not going to detect y dependence as a function of x. Right? So as long as the x's have some motion, you're fine. What does this quantity look like here, the sum of xn squared? Does that look like anything we've seen? Not quite the variance. The second moment. So if I assume each xn is chosen with the same probability, this is going to give me the following matrix. The sum n goes from 1 to n of xn squared, the sum n goes from 1 to n of xn, the sum n goes from 1 to n of xn, the sum n goes from 1 to n of 1, times AB is the sum n goes from 1 to n of xn yn, the sum n goes from 1 to n of yn. As long as the determinant of this matrix is not 0, it's invertible. If I assume all the xn's are taken with the same probability, if I put in a 1 over big N factor for each one of them, this would then become the second moment. So if I look at the determinant is the sum of xn squared, the sum of 1, minus the sum of xn squared.
Wait, sorry, how did you get the matrix again?
I'm just pulling out the a's and the b's.
Okay.
Right? This is just times a will give me this. So now, I want to interpret this in terms of the variance. If I put a 1 over n here, then that's the second moment. So, if I do n squared, the sum xn squared 1 over n, the sum of 1, 1 over n, minus the sum xn 1 over n squared, that's the variance. It's the variance of the sequence x times n squared. So this would just be n squared times the variance of the sequence of the xn's. So as long as I don't choose all of my xn's to be identical, the variance will be positive. And if the variance is positive, the determinant is greater than 0, so the matrix is invertible. So this is why I love the method of least squares. It gives you an explicit formula for A and B in terms of the data you observe. In terms of the values you start at and the outputs you observe. It's an explicit formula. It follows immediately from calculus and linear algebra. The problem right now is it seems like it only works if we have linear relationships. So the next thing to do is, well, what if we had something that depended on 3 things or 4 things or 5 things? Could we do that? You know, how far can we generalize this? And so it turns out that the method of least squares is pretty robust in that sense. All that matters is that it's linear in the unknown parameters. So I'm not going to go through the algebra, but generalization So let's say we predict yn is f1 of xn plus f2 is a1 f1 of xn plus a2 f2 of xn plus dot 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 plus ak fk of xn. I don't care what these functions f are. I will have something linear in the unknown parameters a. And if it's linear in the unknown parameters a, I can differentiate with respect to the a's and get a nice linear relationship. I'll get yn minus the sum kappa equals 1 to k, a kappa f kappa of xn squared, and then sum, and it goes from 1 to n. So the only thing is, instead of having a 2 by 2 matrix, what do we get? Yields what?
K by
K by K matrix. Now it's more interesting. Will that K by K matrix be invertible as long as you're not an idiot? Okay. Probably my best picture of an idiot is the back cover of a Mad magazine years ago. Where's Waldo for complete morons? He's in the desert. And so, it's essentially, in the 2 by 2 case, that's essentially what you have to worry about. Do you choose all of your values to be the same? I want to see how the gravitational constant depends on the inclination of my plane as I roll my ball down, and I'm always going to roll it at 20 degrees. Well, you're not going to get any dependence when you do something like that. But what about the 3 by 3 case? That's a little bit more interesting. Okay? So one thing is, we can now get more general relationships. If I can have strange functions, I can have sines, cosines, exponentials, no problem. But I need to be linear in my unknown parameters. Can somebody give me a famous physics law? Okay. You've been volunteered.
F equals ma.
Okay. So unfortunately, everything in f equals ma occurs to exponent 1. Can you give me a physics law of force that has an exponent other than 1?
What do you mean? Like,
Gravity. So what's gravity? I'm sorry? F is equal to g m1 m2 over r squared. Right? This is the force of gravity. Right? So the question is, how do you get 2? There's a beautiful geometric argument by Feynman as to why it's 2. And what he said is, we live in a 3-dimensional space. Imagine you have a sphere. What's the surface area of a sphere of radius r?
4/3.
4 pi r squared. So that's the surface area. We'll edit it out later, don't worry. The volume is 4/3 pi r cubed. The surface area is actually the derivative of the volume, which is a nice fact. If you imagine you have something in the center that's providing yankage, the force you feel is going to be proportional to how much yankage hits you. Okay? Well, the total yankage is going to be constant as you go to a larger sphere.
The only time yank has ever been used by Professor Miller in any context other than derogatory.
Right. Well, no, because I would never call a Yankee fan a Yank. So if your sphere, yes, but not on video. So if your sphere has radius r, the surface area is 4 pi r squared. If the total yankage is going to be constant, then the amount you're feeling is going to go down as a function of 1 over r squared. So if you take like a small piece of metal over here and you put it out further over there, it's going to feel less. If you look at the rays coming out, the density is going to be smaller further out. And so you would get that the force is proportional to 1 over r squared. So 1 over r squared times 4 pi r squared is constant. So this is just a really nice geometric argument. In a 3-dimensional world, gravity should be like r squared. The problem is, what if we don't know this? What if we try to observe some data and try to find the best fit exponent? So maybe we believe force is some constant times r to the a. and we want to figure out what that A is. I'll use alpha for now. Can we use the method of least squares to find the best fit value of alpha? Yes or no?
Not the way we just did it.
Not the way we just did it, right? We need something to be linear. We need it to be linear in the unknown parameter. This is exponential in the unknown parameter. What can we do?
Take logs.
Take logs. Excellent. Right? Everybody take an M&M as you leave. And of course, take a log as you leave as well. Right? So let's let y equal the log of f. Let's let x equal the log of r. If we take logs, we get the log of f is the log of k plus alpha log of r, or what do we get? We get y equals alpha x plus b. So I'll let b equal log k. Actually, I could have called that a from the beginning. And we've made the relationship linear. The method of least squares is powerful enough to predict the best exponents in relationships like this. Okay. As a nice example, you don't have to turn it in. I want you to spend this week, going over issues you have, things you want to study more in this class. How many of you know Kepler's 3 laws? If we had a little bit more time, I would talk a little bit more about them. One of his laws is planets travel in elliptical orbits about the sun. Another is you sweep out equal time and equal area and equal time. So the amount of time it takes the planet to go from here to here, if that's the same as the time from here to here, these areas are the same. And then there's the third law. And the third law is something like the period of the orbit is proportional to the square of the period. I think the square of the period is proportional to the cube of the length of the semi-major axis.
Yeah, something like that.
It's either that or the other way around. And it's, one of them is cubed, one of them is squared. Okay? Absolutely amazing that Kepler sniffed out this relationship. This is before calculators. I think it's even before grad students. You're doing all the algebra. And he saw this relationship. That basically period squared is some constant times major axis cubed. Well, we could rewrite this, of course, as just to the 3 halves. Because you can always adjust so that, one of the powers is 1. And now we can use the method of least squares. So if you want, I've actually posted the data for the periods and the length of the major axes for the planets in our system. I can't remember if I have included Pluto or not, because I first started giving this talk back when Pluto was considered a planet. And so I don't remember if that's still there. Pluto is no longer a planet. Pluto is now a dwarf planet. No, they're not. Dwarfs are half a person.
Indoor planets are half.
Make sure you edit that out.
It was so much fun teaching at Williams while it lasted. So for the last few minutes, I want to talk a little bit about Zipp's law. We've got about 5 minutes, so you guys are going to have to move fast. So here are the 25 most populous American cities from a few years ago. Okay, you can probably figure out which city is which, at least in the very beginning. There's also a definite question of what do you define as the city? And what do you define as the metropolitan area? So if you plot this, you get a nice relationship like this. So this is a plot of the population of the city versus its rank. Most populous, second most populous, third most populous. If you want to try to fit a curve to this, it's not so easy. But if we take logs of the population, still doesn't look so good. But if we do a log-log plot, all of a sudden it's pretty good. What does this look like? A linear relationship. It looks like a line. So, here's the plot of the 100 most populous cities from the source of all wisdom. If you do a log-log plot, again, it's pretty good. And so, what I thought I would do for the last few moments I think we have a very small amount of time left, is to give you another example of a linear relationship. So there's the size of cities. And when we do a log-log relationship for size of cities, it's very nice. Okay, I can do two more. It's a very nice linear relationship. You can also look at frequencies of words. And this is something that's a little bit on my mind as my kids are learning how to read. And I'm learning with them. And so here's a plot of the most common English words and their word counts. Now again, there's different metrics as to what's the most common. Are you doing Schwarzenegger movies? Are you doing Shakespearean sonnets? You will get different counts depending on which one you use. Okay? Schwarzenegger has a huge spike at, I think, back. If you take a log plot, log plot, it's a really nice linear line. So I thought for fun, I would see how well you guys could do for the top 10 most populous words in English.
Populous was often used.
I'm sorry? So I'm going to split the class into two. Factions. So we'll be right here, right between you guys. So you guys are team A, you guys are team Alpha. Alright, this way nobody feels bad about being the second letter of the alphabet.
Screw the Greek alphabet.
Alright.
Whoa.
Well,
Nice.
team rivalry, right?
Alright. Well, since you've gone on that, then you guys get your choice. So how many of you have seen Family Feud? If we had more time today, I would have done a little bit more. We're not going to have the buzzer. Oh, we'll have the... Do you want a buzzer?
Yes.
Alright, come up forward. I need two people really fast, really fast.
Alright, let's go.
Quickly. I need somebody else. Alright. 100 most populous words on my computer. I want the most popular in 10. Ready? Yeah, go.
A.
A. A is number 4. 3 words beat it.
Yeah, come on.
Quickly.
Oh, the.
That was number 1. Do you want to play or pass?
We want to play.
Okay, you've got to play fast.
Okay.
3 strikes and you are out.
Okay.
So
We need words fast.
is.
And
We have no. Let's start with is. We'll take
That's
is.
Alright, is
yeah, I
is
think
number 7.
Yeah, pretty sure and would be there.
I don't know about and.
And is yes or no?
Yes.
Okay, fine. And.
And is number 3.
Good job.
Guys, get ready for
I
the
would say
steal.
I, right?
I. No. We'll say
I.
I.
I is number 20.
okay.
First strike.
Oh.
For first strike, but
Um.
okay. How about R? Right?
Yeah.
Well, is 7.
Is
But R is the conjugation where.
B.
Oh, B.
B. No.
No,
B
no.
isn't used that often.
We're running out of time. 3 seconds. I need an answer.
Oh,
A.
A.
Yeah.
It.
It. Yes, just makes it a 10.
And then you. How about
Oh,
you?
yeah, you.
You.
The sheep
No.
or the person?
The person.
The sheep.
Still a few left.
Oh, do we have to get
We're not doing spoken English.
Let's try
That. That.
That's possible.
That's.
Yes or no?
That.
That.
Yeah.
Yes.
Get ready for the steal. There's not
But
many
this
left.
R. I think
R.
R.
Number 15.
I'm not sure if that's 9, do you think this is more popular?
No.
Yeah.
'Cause that has like the use and indirect statement. 2. Yeah.
If anybody
Two.
has to
Two.
Two. T-O.
T-O.
Oh,
T-O
and
is
then
fine.
how about 4? F-O-R. That's
4.
4.
Yeah,
F-O-R.
F-O-R.
If we get that, that'd be pretty sweet.
oh.
Ah.
Oh.
You did really well. 1, 2, 3, 4, 5, 6, 7, 8. That might be a record for one of my classes.
Let's see if these
Okay,
fools
I
can
got a
steal it.
steal. We've got 2, and we've got 6.
What's this?
I need an answer. 3 seconds.
That's one.
Is that your final?
Yeah.
Ooh,
Yes!
No.
Oh yeah.
Comes in.
Yeah, I totally forgot about that word.
Yeah.
The other one.
That's a weird one.
The other one is in.
Oh.
In.
Preposition.
I guess you have to do the Family Feud thing where you go
So
like
extra M&Ms for everybody on that side.
where you all cheer.